Hey guys, it's Mr. O'Reilly, and today we're going to talk about wave properties. So last week we talked about different kinds of waves and the parts of waves, and so today and this week we're going to talk about the different properties of waves and how you can measure waves. And so we're going to be using some numbers, and in order to do that, we're going to talk about mechanical waves specifically. So mechanical waves, if you remember from last week, are waves that require a medium to travel through. So there are two different kinds of mechanical waves, and on my board right now, I have one specific kind of mechanical wave. Pause the video for a second, see if you can guess what kind of wave this is, and then press play again and see if you got it right. So now that you're unpaused, you can probably have guessed that this is a transverse wave. So transverse waves, if you remember from last week, they have a crest, which is the top of the wave here. So all these different points up top here. They all have a trough, which are all these points at the bottom here. And then they pass through what's called the resting point, which is where the x-axis on this coordinate plane is. So here's your resting point, your crests, and your troughs. So not only do we have crest, trough, and resting point, but we can use those to measure different properties of waves. And so if you did your reading in your lesson outline this week, you're probably kind of familiar with these words already. So over here we have amplitude, which we measure in meters. We have wavelength, which we also measure in meters. And then we have frequency up here, which we measure in hertz. And so as we go through the notes today, we're going to be talking about these three guys in more depth. And so I don't have any notes for you to take because it was a lot of drawing, and I figured it was more trouble than it was worth. So if you just kind of watch and listen to this video, you'll get all the information that you need. So let's get started. I'm going to refer back to this this transverse wave as we move through the notes here. So just have this in mind, okay? All right. So the first term we're going to talk about, and the first term that you learned about in your reading, is called amplitude. And so amplitude is simply the energy that travels through a wave. And so we're talking about mechanical waves. It's not to say that electromagnetic waves don't carry energy and they don't have these measurements. It's just easier to see when we're talking about mechanical waves. So amplitude is the energy that travels through a wave. It's I should say it's the amount. So I'll add that in there. And like I said, you can measure that in meters. And so the larger the amplitude of your wave, the more energy is traveling through the wave. So the larger the amplitude, the more energy is traveling through waves. So if you just ignore wavelength for a minute, we'll get to that in a minute. But if you look at this one here, amplitude, you can see how amplitude is measured. It's measured from the resting point to the crest of a wave. Conversely, you can also measure it from the resting point to the trough as well. So either one, but don't go all the way through. You don't want to go from trough all the way down or from crest all the way down to trough. That's not right. So it's resting point to crest or resting point to trough. And it's just a simple measurement in meters. It's a distance. So if we go back to our original diagram here, our coordinate grid, we can measure this one, and I'm going to have you measure this one just by using your eyes. It's pretty easy. So go ahead and pause the video again. See if you can measure this transverse wave, the amplitude of that wave in meters. So go ahead and pause the video, and then I'll give you your answer. Okay, now that you're unpaused, I can give you the answer. And the answer for this particular amplitude for this wave is 6 meters. So if you measure, and this is 0, if you measure from the resting point all the way up to the crest, we go 1, 2, 3, 4, 5, 6 meters. So the answer is 6 meters. Same thing if you measure from the resting point to the trough, you get the same thing. 1, 2, 3, 4, 5, 6 meters. So pretty easy stuff. It's just simple distance measurement. So if we go to this next slide here, um, if you add energy to a wave, and you can add energy or remove energy from any wave depending on how strong your vibration is through the wave, um, you're gonna get a different amplitude. So if this is our resting point right here, and this is our crest, and this is our trough, if we add some energy to this wave, well, you might expect that the wave is going to get bigger, and that's exactly what happens. So if I draw another line here, if we add energy to this wave right here, then my crests and troughs just should get bigger, and they do. So should look something like that. And that's not perfect, but whatever. So here is our amplitude for this wave over here, and then here's our shorter amplitude over here for this wave. So as the energy increases, we should get bigger crests and bigger troughs. And here's an example of that down here. Here's your low energy wave with kind of short peaks and valleys, short crests and troughs. And then if you have a more powerful, more high energy vibration, then you're going to get higher peaks and valleys, higher crests and troughs as it moves through the resting point. And that's amplitude, not too much more to go over there. Actually, there is more to go over. So if we're talking about transverse waves, we have another type of mechanical wave that we need to talk about, and that would be our longitudinal waves. Can't believe I forgot about that. So longitudinal waves, they also you can measure the amplitude of those as well. And so if you add energy to a longitudinal wave, if you recall, this part here, this part where there's spaces between the wave, that's called a rarefaction. And then the part between where the wave is stuck together here, that's called a compression. And so if you add energy to your longitudinal wave, what happens is that you get more spread out rarefactions, and then more tightly packed compressions. This is an awful drawing. So if you add energy to a longitudinal, I gotta draw the bow. There we go. Perfect. So if you add energy to a longitudinal wave, what happens to that longitudinal wave is that you get more spread out, rarefactions and tighter compressions. So you can kind of see that here as well in this little diagram. Here's a lower amplitude longitudinal wave with kind of middling rarefactions and compressions. But if you add energy to your wave, if you add more energy to that wave, then you're going to get more spread out rarefactions, and you're going to get more longer and tighter compressions. All right, so now we're done talking about amplitude, and now we are going to talk about wavelength. So wavelength is just like it sounds. I'm going to show you this kind of out of order. I'm going to show you a couple of pictures of wavelengths, and then we're going to talk about them and go back to that diagram. So let's talk about the transverse wave wavelength first. So transverse waves, again, they have crests and troughs, to measure wavelength, it's another distance measurement. So it's another really easy one. So it's just like amplitude. So amplitude is a distance measurement on the y-axis, and wavelength is a distance measurement on the x-axis. So wavelength, you measure wavelength not from resting point to crest or resting point to trough, but you measure it from crest to crest, or you can measure it from trough to trough. I prefer crest to crest, and that's probably how I'd want you to do it, just so we can all be on the same page. So crest to crest is our wavelength measurement for transverse waves. So again, let's go back to our diagram. And so we have our transverse wave here. We have a whole bunch of them. And so if you measure wavelength from crest to crest, go ahead and pause this video and see if you can determine the wavelength of this particular transverse wave. All right, now that you're unpaused, I can tell you the distance, the wavelength of this particular wave. If we measure from crest, here's one crest, to another crest here, and we count, there's 2 to 3, 3 to 4, we get a wavelength, I should type that in, we get a wavelength of 2 meters. So we have 2 meters here, and that makes sense because if we count the number of crests, or the number of troughs rather here, you get 5. And 1, 2, 3, 4, 5. If you multiply 5 times 2, you get 10, and that's the distance of our coordinate plane in quadrants 1 and 4 here. So 2 meters per wavelength, and we said our amplitude was 6 meters, right? So I'll just put that right there. So we have an amplitude of 6 meters, and we have a wavelength of 2 meters. So if we go back now, so what does that look like, generally speaking, if we're not calculating? Well, a short wavelength transverse wave kind of just looks like almost like a compression. So if you're looking at short wavelengths, you're looking at wavelengths that are relatively small. So if I just draw a bunch here, they're like relatively small waves like that. And if we're talking about long wavelengths, we're talking about wavelengths that look more like this. And so again, if you measure wavelengths from crest to crest, you can see that this line here is definitely shorter than this line here, right? So here's our short wavelength, here's our long wavelength. And then, of course, we have crests up top, troughs on the bottom, and our wavelength right here. So sometimes, by the way, I'll do a shorthand for wavelength because that's a long word to write. And the shorthand for wavelength is this symbol here. It's called lambda. So here's our wavelength here. Here's our wavelength here, symbol lambda, okay? So that's wavelengths for transverse waves. So how about longitudinal waves? So this one's a little bit tougher, but if you measure wavelengths for longitudinal waves, for compression waves, you measure from the same spot of the compression or the same spot of the rarefaction. That makes sense because you're measuring in transverse waves the same spot of the crest to the same spot of the next crest. So if we draw a couple, so here's a short wavelength. So if we measure from this part of the compression, the very end of the compression, then you just measure to the very end of the next one. And then here's our wavelength, lambda. So if we have a long wavelength, here's our first compression, here's our rarefaction, here's our next compression. And so here is our wavelength. If we measure from the very end of this compression to the very end of the next one, here's our wavelength. And you can see that's a very much a longer line than this one. So short wavelength, for longitudinal, long wavelength for longitudinal. So what you're looking for, and it makes sense, what you're looking for is bigger compressions and bigger rarefactions are going to obviously give you a longer wavelength. Last but not least, we're going to talk about frequency. So frequency is probably the toughest part to understand, but if you keep it simple, it's not too bad. So frequency is pretty simply, it's the number of waves that you see. We'll just keep it at that. So it's the number of waves that you see. And so if you just look at this diagram here real quick, we can see low, medium versus high frequency. So the more waves that you see, the higher your frequency. So if we look at this and we count from crest to crest to crest, so we have 1, 2, and then a half. So this is 2.5 waves that we're seeing. If we count this one, we have 1, 2, 3, and almost 4 here. So this is almost 4. So the frequency is higher. And if we look here, we can see 1, 2, 1, 2, 3, 4, 5, 6, 7, and then a little tail here. So we have about approximately 7 wavelengths here. So we go from 2.5 to almost 4 to 7. So low frequency, medium frequency, high frequency. And so if you notice, the higher the frequency, the more number of waves that you see, the shorter the wavelength is going to be. If you remember, wavelength is lambda, and it's a distance from crest to crest. So this line is longer than this line, which is longer than this line. So as your frequency goes up, your wavelength goes down. And if you remember from math class, which you may or may not remember, that's what's called an inverse relationship. So I'm just going to write that down. So we have an inverse relationship with wavelength. So as the wavelength goes up, the frequency goes down. So wavelength is longer, so we have a low frequency. As the wavelength goes down, short wavelength here, the frequency goes up. So inverse, that's what inverse means. It means as one goes up, the other goes down, kind of like a seesaw. For the unit of measurement, the SI unit for frequency is called the hertz. Is named after the guy that figured out the calculation, which we'll talk about later. And so the definition of the unit for the hertz, so the definition of this particular guy right here is really easy. It's the number of waves per second. So the number of waves per second will give you the number of hertz there are in your wave. So again, one more time, we'll go back to the original diagram and we'll take a look at it. So if we pretend that we had these waves, this big chunk of the x-axis is 1 second. If this is 1 second, all we have to do is count the number of waves that we see. So let's pretend that this wave passed by a spot in 1 second. So we count the waves, and we already did that. We counted the waves. We had 1, 2, 3, 4, 5 waves. And so if there's 5 waves that pass by in a second, then the frequency is going to be 5 hertz. So really, really easy. It's just whatever it is divided by 1, which is can't get any easier than that, right? So we have 5 hertz because 5 waves passed by in 1 second. So if we just pretend that this took 1 second for this wave, this vibration to pass by a certain spot, that's our frequency, 5 hertz. And so again, to cap it off, if we have a rapid vibration, we're going to have a high frequency, right? So the faster like that you bang a drum, right? The faster that you bang a drum, the more vibrations that there are going to be, which means the number of waves that you're going to see is more if you're looking at a sound wave, which means the faster that you hit the drum, the higher the frequency that drum beat is going to be. So that means high frequency, and again, that means low wavelength. And it's just the opposite for a slow vibration. Slow vibration is going to give you low frequency and a high wavelength. So it's going to be a longer wavelength. So this chart illustrates it pretty nicely right here. So let's make this bigger. So if we look at this, here's our short wavelength. Again, our lambda from crest here to crest here is shorter than this crest here to crest here. Our lambda, our wavelength is shorter up here, longer down here. So it's just kind of like logical, right? The shorter your wavelength, the more you're going to be able to fit on the same distance. So if there's small wavelengths, you're going to be able to fit a lot more of them in. It's like you know medium eggs versus large eggs versus jumbo eggs, right? You can fit a lot more in the same spot in the same size carton of medium eggs than you can fit jumbo eggs. That was an awful analogy, but best I can do. So short wavelength, high frequency, long wavelength, low frequency. That's all you have to know. It's called an inverse relationship. And so we measure frequency in hertz. So we're not going to do this part. I think I gave you enough information to kind of chew on for this week. So the main focus for this lesson is those 3 vocab words that we kind of talked about and just went over. So amplitude, again, just to review, amplitude is just a distance measurement of a wave from resting point to crest, and that's measured in meters. Wavelength is a measurement from crest to crest, or if you're talking about a longitudinal wave, it's rarefaction to rarefaction or compression to compression. And that's also a distance. It's measured in meters, of course. And then frequency is the number of waves that you see per second, and that's measured in hertz. And that has an inverse relationship with wavelength. So the higher the wavelength, the lower the frequency. So I'm going to post another video in the next day or two talking about wave speed. And that's going to be extra credit. So if you watch that video and you do the little extra credit problems that I have in them, I'll give you a day off of or a different day off for another day's work that we'll have coming up later on in the year. But yeah, so look for my wave speed video in the next day or so, and we're going to talk about how we can calculate wave speed, and we'll do some practice problems together. So that's it for now. If you have any questions, just contact me, let me know, and I hope that was helpful.